So hello everyone, in this video we are going to cover D2, that is stellar characteristics and evolution. So let's get started. So first we will talk about the stellar spectra. The light that we observe from coming out of a star is basically can be shown in like a black body curve. So you will see that this is a black body radiation curve. And what's the unique about black body radiation curve? It is specifically uh, plotted. There is an intensity of this black body radiation, intensity versus wavelength graph, and this is a black body radiation. A star can be considered as a black body because it is radiating all the energy at a particular temperature. Now, the one thing that we observe is the peak brightness. So So there will be a peak intensity, like the maximum intensity is observed at a particular wavelength. So we will observe a star in a range of a wavelength, and we will see that the intensity at every wavelength varies, and we will get a wavelength which correspond to the peak of the intensity curve. Now there is something that we call as Wein's displacement law. According to Wein's displacement law, the peak wavelength of a black body radiation curve is inversely proportional to the temperature of the body that is radiating. So temperature of radiating body. Now this in terms of astronomy, this is basically the surface temperature of a star. Surface temperature of a star. And this is a peak wavelength that we observe. It means that it is inverse proportion, which means that if the star is like a higher side of a spectrum, so the red color has the visible light of a red light is basically having the greater wavelength. So if the star is looking like a red, then its temperature probably cool. Temperature is probably less because it is inverse relation. So if the star is looking like blue, then it means the temperature is high enough because blue comes on the lower side of the wavelength. Now we can write this relationship like this, and this is equal to 2.9 into 10 to minus 3 meter Kelvin. So this is something that we call as Wein's constant, which is given in data booklet. Okay. So if they have given you the peak wavelength, you can find the temperature. If they are given temperature, you can find the peak wavelength. Or from the graph also, you can determine the peak wavelength. And as you can see, the graph, the intensity starts to drop down as the temperatures decreases. Okay, but you can see that the peak wavelength will be increasing if the temperature falls down. The another evidence that we observe is basically the absorption spectrum of a star. So we did not just look at the intensity of the light that is coming out of it, but we also observe the absorption spectrum. In this absorption spectrum, it gives the chemical composition of the star, where the black lines specifically indicates lines are the wavelength corresponds to wavelengths that are absorbed by a particular molecule, that are absorbed by molecules. Okay, so we can identify which molecules are present, which elements are present. Okay, and from this absorption spectrum, and we can determine what is the chemical composition of a star. So what we see is that in a main sequence star, there is abundance of hydrogen. So almost there is like 70 to 80% of hydrogen, and remaining percent is like 25% of helium, and the remaining 5% will be the other elements, other nuclei. Okay, for a main sequence star. Now, in some sequence star, what you will see is that the hydrogen spectrum, hydrogen lines are not seen. The reason why hydrogen lines are not seen is basically in some cases the radiation usually ionizes the hydrogen. So ionizes means it knocks out the electrons from the hydrogen atom. So as the electrons are knocked off, there is no particular absorption that is happening, because for absorption you need if this is a nucleus, you need an electron to absorb that energy and to go to higher energy level. Okay, so if there is no electron present, then you won't find the absorb that hydrogen atoms, those which are ionized in a hydrogen spectrum on this in the absorption spectrum. Okay, so what we also do is we create spectral classes. Spectral classes are dividing the stars on the basis of their surface temperature and the color. So the classes are given as O. So these are the spectral classes and each corresponds to a particular color. So these are towards red side of the spectrum, these are towards blue side of the spectrum, and then it goes along like this. So blue ones are the hottest, and we usually draw a Hertzsprung-Russell diagram, that is HR diagram, to explain this phenomenon. You can see that. So this graph is plotted in terms of luminosity, but this is not just luminosity, this is luminosity in terms of luminosity of our sun. Luminosity in terms of luminosity of our sun. So this L naught is nothing but luminosity of our sun. So this, so what we plot here is the ratio L by L naught. So that's the reason why where there is one, we see the luminosity our sun we will find, which belongs to a main sequence star, and the surface temperature of our sun is 6000 Kelvin. Now, what you need to remember, most of the time they will ask you to draw main sequence. Now, main sequence extend like a diagonal, and you need to remember that the diagonal, the whatever this line you are drawing, is should be passing through the 1 and 6000 Kelvin mark. Okay, most of the students just they draw the shape like this randomly. It doesn't make sense. It has to be passing through a particular point in a graph. Okay, now you will see that you will find all the red giants on this side of the spectrum, which are much bigger in size. Their luminosity is higher because their see luminosity depends on area and the temperature. So the area is bigger. That's why the luminosity is bigger. But the temperatures are small. So for the red giant, the temperatures are small. You can see that the surface temperature decreases in this particular direction. So the luminosity is high just because the size is big. Now there are also blue joints which are bigger as well as they are hot. Their temperature is also hot, so that are blue joints, and those comes on the main sequence star. Okay, you can see the white dwarf which has higher temperature but smaller luminosity just because their size is smaller. They are just core of a Death Star. Okay, and you can see the red dwarf which are coming here. Okay, so this is how you should able to distinguish it in HR diagram. You can see different row like sizes of the this R naught is the radius of our sun. So you can see along that direction it will be 100 times the radius of our sun. So you make sure this and you should also remember where the CPITS variables belong, a little bit above side of the spectrum. Okay, and it is stable instability region, and that's the reason why we will the luminosity of the silhouette star keeps on changing. Now we will also learn about the mass luminosity relationship, which is given as luminosity is directly related to the mass times 3.5. If the solar mass or the mass of our sun is given, or the luminosity is given in terms of our luminosity of the sun, so this is the ratio we can write this as like this, where m naught is the mass of our sun. Okay, so this relationship is useful, and this relationship is only true for a main sequence star. So basically, if this relationship is not true, then we can test. Then we can say that the star does not fit into a main sequence, and we can, if we know the luminosity and the masses, we can verify whether the star belongs to main sequence or not. Now we'll talk about Cepheid variables. Now Cepheid variables are the stars whose luminosity varies from maximum to minimum periodically. Okay, so if I plot luminosity versus time graph, then the luminosity rises not from zero but a certain value, and then it sharply rises and falls slowly. It sharply rises and falls slowly, and like this. And this is the one time period. This time period can vary from some weeks to months. Okay. Now, why does this happen? Why the luminosity of the star increases? So the mechanism is such that when as the radiation of this star rushes outwards, it the radiation ionizes the helium present in the atmosphere of the star. Okay, ionization processes like this. So basically, if there is an electron then the radiation knocks out this electron. Okay, so that the helium nucleus is without electron now. Now the freed electron increases. So free electron moves and collides more, and thus the temperature of the atmosphere increases. Okay, so temperature of the atmosphere increases, the pressure increases, and thus the at star expands more, increasing the luminosity. When all the helium is ionized, the radiation escapes the atmosphere. Okay, the radiation escapes the atmosphere, and what happens is like the atmosphere starts cooling down, and the helium recombines with the electrons. So this is how the cycle, and as it recombines, the luminosity decreases. Okay, so this is how the process works, and by knowing the exact, so the luminosity, the average luminosity that we calculate, there is a direct relationship between average luminosity and time period. Okay, so by calculating the time period, we can calculate the luminosity, and by using this formula, luminosity and apparent brightness formula, we can calculate the distance. Okay, so that's why the secret star are used as something that we call as standard candles. So whenever we see a secret star in like a distant galaxy, okay, that star's luminosity keeps on varying, and that helps us to determine the distance, okay, from the faraway galaxy. Now we will talk about the stellar evolution. The stellar evolution is very important process. So how does a gas, a dust and gas cloud converts into something that is a protostar? So usually this process happens when uh, gravity, like some masses come closer because of gravity, and the gravity keeps on increasing because more and more masses getting attracted towards each other. Okay, so as the gravity increases, okay, the gravitational potential energy increases, more and more mass will start accumulating. Okay, and when usually the gravitational potential energy of the gas cloud exceeds the average kinetic energy of the gas molecule, average kinetic energy, then the stars will start collapsing under own weights. The mass starts, or the gas cloud, not mass, but the gas cloud starts collapsing under its own weight. Okay, under its own weight. Now, as it's collapsed, the temperature inside increases, and when the temperatures are high enough, the fusion reaction starts. Okay. Now, as the fusion reaction starts, there will be the gravity that will be pushing inwards, gravitational potential that will be gravitational force will be pushing inward the mass, while the radiation will be pushing outward. And there is a tug of war between this. Protostar is something where just the fusion has started. The main sequence star will be in equilibrium. A mean sequence star is defined by the equilibrium between the fusion, the outward, radiation pressure outward is equal to the gravitational pressure inward. So that's the main sequence star, and star remains stable in main sequence star for very long time. Now, usually what happens, a main sequence star, when the for a low mass star, the one important thing happen for a low mass star is that when hydrogen is exhausted, the gravitational pressure start pushing inward. Okay, pushes mass inwards, increasing the temperature. And as the temperature increases, hydrogen gets fused into helium. And if the temperatures are more high enough, it will fuse into carbon. So for a most part, it is for a low mass star, it is either carbon or it is like a oxygen, is the oxygen core. Okay. So if you take a slice of that core, you will see that there will be some oxygen, there will be some carbon, there will be some helium, and some hydrogen, like that. So the heavier nucleus are start forming. Now, as heavier nuclei are fused, more radiation rushes outward, which expands the outer layer of the star. Turning it into a red giant. Red giant. Okay. Now you will see that this is a red giant. Well, this is a core, while this is a red giant where radiation that is pushing it. Gravity is trying to push the core inward. Okay. But In a low mass star, there is not much mass available to fuse further so that higher element than oxygen are not formed. The outer layer then eventually escapes as a planetary nebula when the oxygen is formed and then there is no energy enough to fuse further, so all the radiation will be rushing outwards, leaving the core of the star to be as a white dwarf. So this is a core mostly made up of carbon or oxygen. Okay, and this is stable because of the electrons can't be like electrons have fixed energy, they can be in a fixed region. So no two electrons can occupy a fixed space. Okay, so that's a called as Pauli's exclusion principle, which prevents electrons to occupy the same energy level. And that's the reason why the electrons degeneracy pressure balances out the gravitational pressure. Okay, so that's why it is a pressure. White dwarf is stable because of the electrons degeneracy pressure. Okay, eventually the white dwarf will cool down and become a black dwarf. So on a main sequence star, you can draw this path like from a main sequence, it will leave, it will go into red giant. Before it goes to the red giant phase, there is a flash of helium flash, something that we call like when the helium starts forming. And then again, it will go like this. And then it will come from the red giant, it will come to white dwarf like this. Okay. So we can draw the path like this. Now, there is something that we call a Chandrasekhar limit. So according to Chandrasekhar limit, if the mass of the core of the star is less than 1.4 solar masses, like 1.4 times the mass of the star, like our own sun, okay, then the star becomes, after death, it becomes a white dwarf. But if it is greater, if the mass of our core, not the mass of a star, mass of the core of star is greater than 1.4 solar masses, then it can convert into something that we call as neutron star. Now, how does a neutron star is formed? Basically, in this red supergiant, if you see a core of this red supergiant, you will see that heavier nuclei like iron, magnesium, silicon, neon, all those elements are forming. Okay, and the energy keeps on forming, and the gravity is so much, it keeps on forming the heavier nuclei. So when the iron is formed, no more fusion is possible because iron has the highest binding energy per nucleon. So iron since have highest binding energy, no fusion is possible further. So the gravity just rebounds immediately. So it tried to fuse, but once the iron is formed, it will just rebound into something that we call as spectacular explosion, that is supernova. Okay, and what remains is the core. That core is mostly iron core. Okay, but since the density is high enough and the temperatures are high enough, okay, all the electrons start fusing with the protons, giving us only neutrons and neutrinos. And these neutrinos, like this, they go out, and what remains is the neutron star, which is having all the neutrons only. So there is no electron degeneracy pressure to hold. So neutron star is even denser than the white dwarf, and this is what the stable. So the neutron pressure usually balances out the gravitational pressure. Okay, so here the strong nuclear forces playing. Now, if there is something that is called as Oppenheimer, Volkov limit, which is like of 2 to 3 solar masses, okay, for the mass of the core. If the mass of the core is less than 2 to 3 solar masses, then it is a neutron star. But if it is greater than 2 to 3 solar masses, this is a mass of a core, remember, not a mass of a star, mass of core. Then it will turn into a black hole where even the neutrons can't prevent, okay, for the gravity to rush further. This is how it starts as formed.